with this lately. There are 4 fundamental forces, and the forces have different scales, right? Some are weaker interactions and some are stronger, but there are 4 of them, and we'll talk about them briefly today, or at least some of them. All right, and so I'm going to make a list. So there are 4 forces, and I want to talk about 2 different things, 2 different characteristics of each of the force. First, I want to talk about the strength of the force, right? How strong, for instance, is gravity? I've already spoiled one of the forces, gravity. I'll write that down. Everyone knows this is one of the fundamental forces. This is what you really spend a lot of your intro physics on, is gravity. It has a strength relative to the other forces, right? We'll talk about that in a minute once I write them all down. And then we're also going to have to talk about, well, think about something has to carry that force. Imagine you have 2 electrons. Right? We know when electrons get close to each other, they repel each other because they're both the same charge. But there has to be, but electrons repel each other even at a distance. They don't have to touch. Right? And same with any other particles, right? As they start to approach each other, there's a force, whether it's attractive or repulsive, that either pushes them together or pulls them together. Right? So there has to be some object that carries that force between the 2 interacting particles, called a force carrier. All right, and it turns out that there's a particle associated with most of them, and we can and in fact most of them have been measured. And I'll talk a little bit about how these force carriers interact today. All right, so gravity, of course, is the first force. We know gravity because that's what keeps us on the ground, right? Gravity is a force between macroscopic objects, right? We see gravity right in the interactions between planets and stars, or humans and the Earth, right? These are macroscopic forces, all right? And we'll come back to that in a second. I want to talk a little bit about, I don't want to get into the details of gravity yet until we talk about the other forces, because gravity is kind of unique. And I'll explain why I can't really talk about a carrier for gravity in a second. I'll explain that. But there are 3 other forces that are much more relevant to us microscopically. Does anyone happen to know any of the other 4 fundamental forces? What's the what do we call the force that attracts a positive and a negative charge? Is that gravity? What is it? What's the name for it?
Attraction.
Well, yeah, but there's a specific name for that attraction.
Between.
Yeah, sure, electromagnetism, right? Of course, magnetic effects and electric effects are the same thing. They're 2 sides of the same coin. So electromagnetism, of course, is the force we are very familiar with, right? That's what binds charged particles together, right? Positives and negatives, magnets, right? And that's what attracts magnets together, right? Electromagnetism. It's very different than gravity. Does anyone happen to know the other 2? You don't have to know necessarily what they do, but maybe you've heard their names before. They have diametrically opposing names, these 2 remaining forces. Does anyone know what they're called? These are the ones you've probably never heard of, because they're not all that relevant to chemistry. But they're called the strong and the weak force. All right, and I'll talk a little bit about what the strong and the weak force are after we kind of talk about these strengths, relative strengths, okay? And these forces, the strong and the weak force in particular, are things that are, as we'll find out, are relevant to the nucleus. They're not really relevant to electrons, as we'll see. But as we'll learn, the strong and the weak force are what cause nuclei to bond together, what keep protons and neutrons together. We'll see in a second. So these are our 4 fundamental forces. Every interaction in the physical universe can be categorized in one of these 4 forces. All right? And I want to talk very briefly about their relative strengths. Right? They're not all the same. Imagine if you have 2 particles. Right? Doesn't matter what they are. They're at some fixed distance from each other. And imagine that we could flip a switch on them to choose which one they're attracted by. Okay? And the question we're going to ask is, how strong is the force, depending on which force we pick at that fixed distance between 2 particles? All right, so what I'm going to do is I'm going to represent them in a normalized fashion. So I'm going to take the strongest one and give it a strength of 1. Not surprisingly, the strongest force in the universe is the strong force, hence the name. And it effectively has a strength of 1. Okay, so let's just say that this is the strongest force. Its strength is 1, so everything's going to be relative to it. And it turns out that you can you can precisely measure how strong the electromagnetic attraction is relative to the strong force. And the number is almost exactly 1 over 137. All right, we'll see that number again, 1 over 137 later. It's a very important number. But the idea is that the strength is actually determined by this number 1 over 137, right? So it's about 100 times, a little over 100 times weaker than a strong force, the attraction between, say, a proton and an electron. Right? The weak force, not surprisingly, is weak. It has a strength of about 10 to the minus 6. Right? So it's about 1,000,000 times weaker than the strong force. Right? Not surprisingly, we don't see the weak force appear very often, because it's very weak. Right? But there are important effects that are characterized by the weak process, the weak interaction, and I'll talk about those that are relevant to chemistry. In gravity, the strength of gravity relative to the weak force is 10 to the minus 39. Gravity is extremely, extremely weak. Right? Extremely weak. So as we'll find out that these three forces, which are all kind of in the same range compared to gravity, they all can kind of, right? They all kind of mix together. They're all kind of interrelated to each other in some extent. But gravity's by itself. Because things that interact between electromagnetic, strong, and the weak interaction, things where these are important, right? Electrons, protons, subatomic particles, microscopic, gravity does not affect them at all. Right? There's very, very little gravitational attraction between two atoms, right? It's basically negligible. Of course, because it's a 10 to the 40 smaller. Okay, so gravity tends to be on its own. Right? And it's an open problem. So and I'll talk a little bit about this, for the last 50 to 60 years or so, physics has been interested in how these three forces are interrelated in the atom, or in nuclear physics. And then there's this other force that, of course, we see gravity everywhere. Right? Gravity is seen at all macroscopic scales, right? We see it between each other, we see it at the planetary scale, at the galactic scale. Right? And it seems like there's a cutoff, right? That this gravitational force is completely separate from the other ones. And that's an open problem in science, is how do these are all interconnected? We can interconnect, as we'll see, electromagnetism and a weak force. The strong force is interrelated to those as well, and gravity is just by itself. Right? So it's still an open question of how does gravity, right? Is there a unified theory, if you will, that connects all four of these together? And that's still an open question. And that's because gravity in and of itself is weird. So here's our four forces. We'll talk about the particles that are associated with these forces. How do they interact in a microscopic system? But we should think about how is this force transferred between two objects. Right? I said that if you take an electron and a proton, which you do in a hydrogen atom, right, they don't touch each other. Right? They're attracted to each other, but they're not touching, they're not colliding. Like, we can even measure the average distance between the two in an atom. But somehow they're transmitting force between each other. And there has to be something that mediates that force. Right? Something that transfers it, right? Like a little messenger, a force messenger from one particle to another. And each of these forces, except for gravity, has one of those. And the carrier for, let's start with electromagnetism, which of course is the most relevant one for us. We'll see chemistry has everything to do with electromagnetism, has a very, very well-known force carrier. It's a very, very important particle. I wouldn't even call it a particle necessarily, but the carrier of the electromagnetic force is the photon, light. Light is, the light itself is what carries the force between interacting particles in the electromagnetic field. Right? So if you bring two electrons together, and you can show this in an experiment, you bring two electrons and they scatter off each other, right? You bounce them off each other. What happens? Well, they emit photons. They emit light. They release that energy as light. Or, for instance, if you take an electron and accelerate it around a circle, like in a big tube, big circular tube, you'll accelerate it, and as it rotates around this thing, it emits light. Right? So as you apply an electromagnetic force to the electron, it interacts with your system by emitting photons. Right? So the light particle, light itself, is what transmits information and force between electromagnetic particles. Right? There's this concept that imagine you have an electron, two electrons far apart from each other that are interacting. Well, you might see them floating in the air, but they're not emitting light. Just imagine they're just sitting in a vacuum by themselves, stuck in position. You're never going to see them emit light. But when you represent the physics of this system and they're interacting and repelling each other, what's happening is one of the electrons is creating a photon very quickly, which is then destroyed when it's absorbed by the other one. Right? So the electrons, these electrons that are interacting, or any electromagnetic particle, they're exchanging light particles between each other. Right? You don't see them because they're not emitted, but they're transmitted temporarily between particles. We call them virtual photons, virtual particles. Right? They're not things you can measure, but the only way to get the math to work and all the calculations to work is to assume that when two particles are interacting via electromagnetism, like a proton and electron, is that they're transmitting photons between each other. It carries the energy. Photons carry the electromagnetic force between particles. The other two, the strong and the weak, also have particles that associate these motions, or sorry, that carry these forces. And the strong force has a very useful, kind of a stranger named particle called a gluon, named after glue. Right? Glue. In fact, what we'll see is that the gluons, the strong force is what keeps nuclei together, partially. Also is what keeps, as we'll see, protons together, the neutrons together. And the little individual components, the protons and the neutrons and all the, as we'll see, protons and neutrons, they're actually composite. They actually have smaller particles inside of them. All of these particles are glued together with these gluons. Right? And it's hard to see gluons, but there have been experiments that show that the strong interaction is mediated through these gluons. And it turns out, interestingly, there's 8 of them, 8 different kinds. Right? You need 8 different kinds to explain how nuclei and stuff bind together. Okay? And that number 8 is very interesting. That was a Nobel Prize winning discovery that there are 8 flavors of gluons. Photons, there's only one kind. Right? There's only one kind of light. But gluons, there's 8 different kinds. They have different masses and different energies. And then the weak force is mediated by 2 different particles. One of them is charged. It's called the W boson. W plus or minus, so there's a positive and a negative one. And there's another one which is neutral, which is called the Z boson. Right? We'll talk a little bit about these. They're very, very, very big particles. They're very rare. They exist for a very short amount of time. And as we'll see, because they exist for a short amount of time and they're very heavy, or they're very energetic, that correlates to a force that's very weak. Because in order for to transfer energy between 2 particles that are mediated by the weak interaction, you have to create a force carrier that's really, really big. And that requires a lot of energy, and so therefore it's very rare. And we'll talk about the scales of the masses here in a minute. Right? So there's these fundamental particles that basically are transferred between 2 bigger particles that are interacting through one of these forces, the photon being the most important one. There's one more force, of course, that I haven't mentioned, gravity. As I said, gravity doesn't have a particle because there is no microscopic theory for gravity. Right? The only way we understand gravity is through the interaction of giant objects, right? Planets and moons and stars and galaxies, right? And so there is no force carrier for gravity because it's not a quantum mechanical theory. There isn't a particle associated with it or a wave. It's a force. It's just a classical force. And so there's really no carrier for gravity. But let's think about how gravity works. And this is what Einstein discovered with general relativity. How if you can't transmit force between objects, how can you have a gravitational force in this context? Well, the way that gravity works implies that there isn't necessarily needs to be a carrier. So the way to think about gravity, a really, really good way to think about gravity is imagine the universe is a giant mattress. All right, it's a big, flat IKEA mattress, really, really stiff. Okay? And it's completely flat. All right? Now, think about just space being 2-dimensional. A mattress is in 3 dimensions, it's 2 dimensions, right? It's a plane. And imagine you take a bowling ball, okay? And you place that bowling ball in the middle of the mattress. What happens? Well, the mattress sags around it, right? The mattress gets deformed, and the mattress bends around the bowling ball. Okay. And so what happens when you place a small test particle, say a little small bouncy ball or something nearby, on the mattress? If it's close enough, that bouncy ball is going to roll into that divot, right? So the mass, the big heavy mass, the big bowling ball, basically distorts, bends space, right, and creates this divot in space, and thus now space is now being curved downward towards the ball, and so things now naturally roll towards the ball, right? So the attraction and gravity isn't due to a particle being exchanged between two things, at least as far as we know, but rather it's due to the fact that what's happening is when you put a heavy mass inside of space, space distorts around it, it bends. And that naturally allows things to be attracted to it, right? It rolls down into that little divot. All right, so just the nature that space-time or space is distortable by mass, right? That you can bend space around a heavy mass is what causes gravity to happen. And unfortunately, well, or fortunately maybe, the way at which gravity does that is tiny compared to the other forces, right? This effect is 10 to the 40, almost 10 to the 40 times smaller than the other effects that we're used to. Right? So it's a very, very, very minuscule effect. But if you have a mass that's, you have a star that's 10 to the 40 times larger than an electron, then gravity becomes significant. Right? So there's no real carrier. Some of you may have heard of a term called a graviton. That's the hypothesized particle to exchange for gravity, but it's never been observed. And I tend to believe that argument is bullshit. I don't think it's really that real. Right? It's never been proven. There aren't any really experimentally testable hypotheses assuming a graviton. So no one's ever seen that, but it probably, there must be something that associates these forces together. We just don't know. So I'm going to put a big fat question mark here. I don't know. Not surprisingly, we're chemists. We're looking at really small things, right? Gravity doesn't matter to us. We're going to ignore gravity. Right? Gravity will never come into conversation in this class. Right? And the question, of course, is in chemistry, well, which ones of these are relevant? Right? Of course, we know electromagnetism must be relevant, right? Because we have a hydrogen atom is a proton and an electron. They're attracted through electromagnetism, so that must be relevant. And we'll see that that's, of course, the case. And of course, light, of course, is relevant for chemistry. Right? We have spectroscopy. Right? We know that things interact very strongly electromagnetically in chemistry because we use light to probe things all the time. So we'll have to ask a question about the strong and the weak force. But I'd like to talk a little bit about those just to give you a sense of the kind of environment or the universe that we live in terms of matter. Any questions so far? Okay. So these three forces generate through interactions a zoo of particles, right? Things that make up the constituents of matter, right? And some of them interact through all of the forces. Some only interact through a small subset of the forces. So I have a nice picture here from Wikipedia. Hopefully it's big enough. Yeah, we'll talk about this. This is what's called the standard model of elementary particles. These are there are many more particles, but these are kind of like the lowest energy ones. You can think of this as like the first row of the periodic table. Right? So these are kind of the most common particles that we see in the universe. And we're familiar with some of them, of course, the electron. And that's about the only one we're probably familiar with, actually. So it's interesting that there's all these, and of course the photon, right? The light. The light, of course, is a particle. We can consider it a particle. And so let's talk a little bit about the properties. I know this might be a little hard to see. I'll try to write it a little bigger for you guys in the back. But each of these particles have a set of properties that are associated with them. And I'll write them down. They're kind of small here. Of course, I'll post this online so you can see it later. But the three properties that we're concerned about are mass, charge, and the spin characteristic, spin. Okay? So there are other properties. Some of the other particles have other properties. We won't worry about those. Okay? So these are the three properties that all particles share. All right? There are some other properties that certain sets of particles share that we won't talk about. Right? There's something called color, for instance, and flavor. I use those terms for a good reason. Those are actually real terms in physics for different types of properties things can have, but we're not going to be worrying about those. These are the three that we care about. So you might notice that these are kind of characterized, kind of split down down this angle right here. So there's this what's called here, they're called fermions, and there's these set of things called bosons. These are very, very, very important characteristics for a particle. And they have a very, very, very simple explanation. Let me put it this way, there's an observable property that's very different between fermions and bosons, just one. And let me explain what that is. So one thing to know about any particle at all is that if you have, say, a gas, right? Let's say you have a box of electrons, right? Let's say you have 100 of them in a box. It is physically impossible for me to say this is electron 1, this is 2, this is 3, right? To name them, right? I could take each of the electrons and name them after each one of you, right? There's the Danny electron and so on and so forth. You can't do that. All particles, every fundamental particle, or any microscopic object, including atoms, are indistinguishable from each other. The only thing I can say, and we'll see this again in this class over and over again, the only thing I can say is how many I have. Right? So if I have a box of 30 electrons, all I can say is there are 30 in there. And every particle is exactly the same from each other. They're indistinguishable. Every microscopic object is indistinguishable from another of the same type. There's really, really important consequences for that. So just to kind of say that in 3 words, is that particles are indistinguishable and there are 2 different types of indistinguishability in the universe. And they fall into these 2 classes, bosons and fermions. Now we'll talk about the specific properties of what a fermion is, a boson is later, because it's important in chemistry. But let me give you a basic sense of the consequences of being a boson or a fermion. A boson has the property that multiple bosons can exist in the same space and state simultaneously. What does that mean? Well, people have shown this experimentally. If you take a bunch of bosons, for instance, there are atoms that are bosons. If you cool them down enough, you can get them in a situation where all of those atoms, they all stack up on top of each other. They all exist in the same space. They're all the same particle, and you have this density of atoms, these bosons, that all exist exactly in the same spot. They all move together coherently, right? They act as if they're one particle, a collective particle, but there are in bosons. Okay, so you can condense them into a single effective particle. You can make a super boson by cooling a bunch of bosons together and making them exist in the same space. If you've ever heard of a Bose-Einstein condensate, which is a very kind of exotic type of matter, cold matter, that's how they work. So a Bose-Einstein condensate is a fluid where all of the atoms exist in the same space in the same state. They all act collectively as if they're one particle, but they're a distribution of particles inside of them. Right? It's a really weird concept. So imagine taking a bunch of bowling balls and stacking them all together in the exact same spot, right? You have a super bowling ball. That's how bosons work. All right, and as you can see, there are a lot more fermions than there are bosons, right? There's only a few bosons. There's the W and the Z's, the photon, the gluon, right? All of the force carriers are bosons. And I haven't talked about this, but there's this other one, the Higgs boson, which I'll mention here at the end of class. Maybe you've heard of that one if you remember about 10 years ago, the LHC discovered this big particle that the press called the God particle. That's this Higgs boson. Right, but as you can see, all the kind of more relevant particles, all the other ones are all these fermions. So what's a fermion? Well, a fermion has the opposite characteristic of a boson. And I'll just write it, only one can exist in a single spot. All right? You've seen this before. When you talk about electrons, I'll write this on the board. Electrons are the most common type of fermion. And this idea that fermions can only exist at only a single fermion of a single type, single state, in a single spot can exist at a time, is the reason why electrons fill into orbitals in the atoms the way they do. Right, so let's look at that for a second. Right, let's look at carbon, for instance. Carbon has a 1s, a 2s, and 3 2p orbitals. And how do we fill the electrons? Well, there's 2 in the 1s, 2 in the 2s, and 2 in the 2p. Right? By writing it this way, I've automatically assumed that the electrons can't exist in the same space. Right? What I mean by space is orbitals. Right? Orbitals in chemistry. Right? So only one electron of one type can exist in one orbital at a time. Right? So when we fill up the 1s orbital, what do? Well, we put an up electron, right? If you remember, these mean that the up electrons mean their spin plus 1/2, and then we fill the electron with a minus 1/2. Right? These are the two colors of electrons, right? The white and the black. Right? The idea is you can only put one white electron in the shell and one black electron. And that's it. You can't put two white electrons in one 1s orbital. Right? The next white electron has to go into the 2s. Right? So this is the Aufbau principle of filling electrons, and it's a direct consequence of the fact that the fermions can't exist in the same state in the same space. Right? That limits us to only having 2 electrons per orbital, because there are only 2 types of electrons, up and down, plus 1/2 and minus 1/2. So that's assuming they're fermions. Now, what if electrons were bosons? Well, if we had electrons, so these are fermions, but what if they were bosons? Well, we would still have the same set of orbitals, but all of the electrons can exist in the same space if they were bosons. So carbon would fill up, well, it's got 6 electrons, right? They'd all sit in a 1s orbital because they can't. Bosons can exist in the same space at the same time. So if electrons were bosons, we'd have no atoms, right? There'd be no valence electrons. Everything would be sitting in the core as deep as possible. There'd be no chemistry at all. Right? Every atom effectively would act exactly the same, right? Because there will never be any. Right? They're all going to be buried deep in the shell. They're going to be really hard to pull out. They're all stuck together. So the difference between carbon and hydrogen really aren't that great. Right? So it's essential for chemistry that the thing that we deal with, the electrons, are fermions, because that's what defines atoms to begin with. Okay. So here's our electron. It's one of our many fermions. We'll talk about the rest of them in a second. You'll notice here's the electron. It has, let me scroll over a little bit. I'll write what it says here. So it says that the charge of the electron, I'll write C for the electron, is -1. Well, we know that, right? The electron provides a -1 charge. It has a spin of plus or minus 1/2, right? That's our color, right? It can be black or white. And then the mass, it's hard to see this here. Let me zoom in a bit for you guys.
Is this for an electron?
Yeah, this is for an electron. Let me scroll over just a bit. You'll see that the mass it writes is in this weird unit, MeV/c². I'm going to convince you that this is a mass. Right? And we can see that the electron has a mass of 0.5. This is what's called a mega electron volt divided by c². Now, why c² is the speed of light squared? So why do we use this for mass? Well, why is this a relevant mass unit, right? It's not kilograms, it's not Daltons, AMU, mole, grams per mole, nothing, right? Turns out to be an energy, mega electron volts. So why are we using that for mass? Well, there's a good reason for it. It's because what does Einstein tell us is that when particles are moving very fast or at very high energy, the mass is proportional to energy, right? E equals mc squared, right? This is for particles moving near speed of light. Okay, so if I take E equals mc squared, I can write this as m equals E over c squared. Right? So a mass of a particle is its energy divided by c squared. Right? Which is why the masses for these particles, I must have kicked my power out, sorry. That's why the masses of these particles are listed in terms of this weird energy unit. And this is just a unit that physicists use to compare things, because some particles you can only see at very, very high energies. Right? So we have to have a scale to compare them all. Right? We can measure the mass of an electron very easily. Right? We can give it a kilogram measurement. But some of these particles you can only see at very, very high energies where things are moving at relativistic speeds. And so it's good to have a comparison between the numbers. And so electron is actually very small, 0.5 mega electron volts. I'll write this on the board. Actually, I'll put it on the screen. Just a sec. I'll give you a conversion factor. So let me just add a new page here real quick, and we'll come back. 1 electron volt, we'll see this unit again, is about 90 kilojoules per mole. And 1 giga electron volt per c squared is about the size of a hydrogen atom. Okay, 1 AMU. Okay, so this gives us a sense of the size of things. Right, so you can think of a 1 giga electron volt as a hydrogen atom, right? Or you can change it to energy if you're more interested in energy scales. I think mass is more useful. Right, so a giga electron volt, 1 billion electron volts has an effective mass of the size of a hydrogen atom, roughly. Okay, so let's keep that in mind. I'll write that here on the board.
AMU or
AMU, atomic mass units. So I'll write that here. 1 giga electron volt over c squared is approximately the mass of hydrogen. Okay, that gives us a nice comparison. Okay, 1 giga. All right, so let me go back to our table. So if we look at the electron is 0.5 mega electron volts. That means the electron is very, very small compared to the hydrogen atom. Right? The electron is about 1,000 times smaller than the proton. It's about 2,000 times smaller, right? If we assume 1 giga electron volts is about the mass of hydrogen, this is 2,000 times smaller than that. Right? So the electron is a tiny, tiny little particle. There are other particles. If you notice, if we go along this row right here, there's another particle that's -1 charge plus 1/2 spin. Another one that's -1/2 charge plus 1/2 spin. Very similar to the electron, but they have much larger masses. Right? The muon is 2,000 times or 200 times the size of an electron, and a tau particle is a couple thousand times bigger. They have the same, very similar properties of the electron, right? They have the same charge and the same spin. They interact exactly the same way for the most part, but they have much different energy scales. You can kind of think of the electron as like a ground state -1 plus 1/2 particle, and these are excited states. Like you can think of the muon as an excited state of the electron, right? Because remember, energy and mass are equivalent to each other. So a higher energy, a larger mass means a higher energy. So the muon, in some ways, is a higher energy electron, like an excited state of the electron, and the tau is even higher than that. Not surprisingly, we don't see taus very often. They're very, very high energy. Can only be made in very, very high energy processes. The muon, however, actually lasts for a very long time. It lasts for about 2 microseconds, 20 microseconds. You can actually make it in the lab. People have in fact made hydrogen where they've taken the electron off and replaced it with a muon. Right, so you have a proton and a muon atom. Not surprisingly, muonic hydrogen has very similar properties to electronic hydrogen. You see the muon. The sun has a corona of muons. It constantly is emitting muons. So they're very common. They come through the space. They come through the atmosphere all the time. A very common particle that you see, but you don't really interact with it too much because, again, it doesn't last for very long and it's fairly high energy. But the universe does make quite a bit of them. There are these other, and so we'll talk about these. Not surprisingly, right? These are all -1 charges. Right? They have a charge, so they interact through the electromagnetic interaction. Right? They interact with protons and negative charges and positive charges. Right? There's other 2 classes of fermions we haven't talked about yet. And if we look at these ones right here, let me zoom in a bit. These ones, these strange-looking purple ones. There are 6 of them. Up, the charm, the top, the down, the strange, and the bottom. Now let's look at their properties for a second. They're also spin 1/2, just like the electron. There's almost everything is spin 1/2, pretty much. But notice that they have fractional charges. The up, the charm, and the top have a charge of 2/3. And the bottom, the strange, and the down have charges of -1/3. These particles do not interact with the electromagnetic interaction. And if you notice their masses are massive. Right? This one's 173 giga-electron volts, right? It has the equivalent mass of 173 hydrogen atoms. Very, very high energy particle. Right? Some of these are a little smaller, but in general they're much larger than the electron. These six particles are called quarks. And quarks are the fundamental particle that interacts with the strong force. So these particles interact with the strong force, and our nucleons, the protons and the neutrons in our atoms, are made up of these particles. So you might notice that the proton and the neutron are not on this list. Right? We think of those as fundamental particles because every atom is made of them. But the interesting thing is that protons and neutrons aren't fundamental particles. They're composite particles. They're made up of quarks. So a proton turns out to be, so I'll write it here. I'll just write it kind of in, I'll write it on the next page. A proton is 2 up plus 1 down quarks. All right, so it's a conglomeration of 3 quarks together that are all stuck together with the strong force. All right, the strong force is what keeps quarks kind of glued together. And let's look at the properties of the 2 up and 1 down system. Let me go back here. I might actually have it. Yeah, that's right. 2 up, 1 down. So if we look at the up electron, the up quark, it has a charge of 2/3. And the down has a charge of -1/3. All right, so what's the total charge of 2 ups and 1 down? Well, it's 2 times 2/3, which is 4/3, -1/3. So the total charge of 2 up and 1 down is +1, just like the proton. All right, so the quarks combine together. It turns out they have to combine together. You can't see a single quark by itself. They have to combine together in pairs or triplets, typically. And the charges add together to create the conglomerate that leads to the charge and the spin of the particle that you're used to. Interestingly, the neutron, very similar. It has no charge. It is 1 up plus 2 down. Okay, so it's got a different arrangement of the up and the down quarks. And let's go back and look at those 2 quarks here. 2 downs gives you a net charge of minus 2/3, and then you add an up to give plus 2/3, the net charge is 0 for the neutron. Right? And it makes a lot of sense. That's why the neutron has 0 charge and the proton has plus 1 charge, is because the combination of quarks that make them lead to those net charges. Okay? Remember that the strong force is really, really strong. Okay, so the proton and the neutron are very strongly bound particles. All right, it's very hard to break. Well, it turns out it's easy to break a neutron apart by itself, but in protons, for instance, it's impossible to break it apart. And one of the reasons why it's impossible to break a proton apart, right? A proton, if you have a bare proton just sitting in the atmosphere, in the universe, just in the vacuum, it will always be a proton. No one's ever seen a proton decay and fall apart into smaller particles. And the reason why is, again, if you think about particles like you do excited states, right? That a larger mass means a higher energy, which means a higher excited state, right? 2 ups and 1 down is the lowest possible energy for 3 quarks together. There's no smaller mass combination of 3 quarks, or rather a smaller mass or a smaller energy, however you want to think about it, that you can generate. All right, so the proton in some ways is the ground state of 3 quarks. That's why it's so stable. However, a neutron has a way to lower its energy. And so a neutron, if you leave a neutron in the vacuum by itself, a lone neutron, it falls apart within about 15 minutes. The half-life of a neutron is about 15 minutes. Right? And a neutron, the only way a neutron can be stable is if it has a proton buddy with it. Right? The presence of a proton stabilizes the neutron. And that's why, of course, atoms have tons of neutrons, and you can build larger atoms with more neutrons, like isotopes, because the neutrons like to stick to the protons because they stabilize them. Right? So the proton, in some ways, is the fundamental composite particle of quarks, this fundamental strong particle. Right? That's why we have so many of them. Right? And neutrons are much rarer by themselves because they fall apart because they're kind of like an excited state of 3 quarks. Right? And there's a lower energy state they can go to, and they will fall apart if they're not stabilized by a proton. Now, of course, you might be asking, I've just listed 2 composite particles, the proton and the neutron, that are made up of the up and down, but there are 4 other quarks, the charm, the top, the strange, and what used to be called the beauty quark, but now called the bottom quark. And the reason why it's changed to the bottom is the top wasn't discovered till way later. Of course, it has a very, very large energy. It's the largest of all of them, 173 electron volts. It wasn't discovered till like 1998. Right? And they changed this from beauty to bottom to match top. Because otherwise it would be beauty and ugly, and it's not very good use for subparticles. So there are other particles, composite particles, that take charm and top and strange and bottom, but they're very, very high energy. Right? You make them in high energy processes and big colliders and stuff like that. But they're not very that relevant. Right? The up and the down and the strange were discovered very early. They're very low energy particles. The charm, the top, and the bottom were discovered much later because they're much harder to make. They're higher energy particles. Okay, so the interesting thing about the quarks and I just want to mention this really quickly because I think it's interesting. If we think about the force between a proton and an electron, all right, and let's say in the hydrogen atom, for instance, so we have a proton here separated by some distance, and there's an electron in there, right? This is what the hydrogen atom looks like. The force, and let's say the distance between them is r. The force between the proton and electron, so F of r, goes as 1 over r squared. Right, just like gravity. Right, you double the distance between the proton and the electron, and the force goes to a quarter of the force. Right, just like gravity. Gravity is exactly the same way. So what about the attraction? Interestingly, of course, this is electromagnetism, right? Of course, EM. Let me save this just so it doesn't crash. All right, what about the force between 2 quarks? So what if we say the force between an up and a down quark? All right, so you have an up quark and a down quark here at some distance r. And the question I have is, how does F of r go? All right, so as I pull them apart, how does the force go? And this is why the strong force is very, very bizarre. And it gives it its name, is that the force gets stronger the further away they are. It scales, I think, as roughly r to the 4/3, I think. So what does that mean? Well, in gravity and electromagnetism, the more you pull an electron away from a proton, the weaker the interaction is. Right? But the strong force is the opposite. The more you pull two particles, like two quarks inside of a proton. So for instance, let's say we want to take a proton, we want to break it apart, right? We want to take that proton and stretch it until it falls apart. The quarks inside the proton will push harder and harder against you as you pull away. Right? It acts more like a spring than it does a force, like an attractive force. It's like a spring. The harder you pull on a spring, the harder the spring wants to come back. And that's exactly what the strong force does. So what it turns out is that because of that, because it's impossible to pull quarks apart, quarks always appear in pairs or bigger. Let's say in packs. They can be triplets, they can be pairs, and so on and so forth. They always show up in packs. If you pull a proton apart, and an up and a down, and the two ups and the down, you pull them apart. Once the proton breaks, you can't break it apart. The quarks actually magically generate new quarks to create a pair. So if you pull an up and a down apart, let me just draw this kind of as an example. So let me just draw it in here. So if I'm going to take an up and a down, and I'm going to pull it apart, when it breaks apart, which it does after a ton of energy, eventually it'll break apart, what you end up making are two new pairs, two up particles, but you make what's called an antiparticle. That's what the dot means. I haven't mentioned this, but almost every particle has what's called an antiparticle. The electron has an equivalent particle called a positron, which has a +1 charge and spin of 1/2. There's an antiproton, which has a negative charge. There's an antimuon, and so on and so forth. So there's these antiparticles. I'm not really that worried about them right now. But what happens is that when you break it apart, you make pairs of quark and antiquark of the ones that break apart. So they're always in pairs. This is what's called confinement. Right? And this is why our nuclei are so rigid and so hard to break apart. Because to break them apart, you have to have an insane amount of energy to break them apart, right? Because it wants to pull against you every time you try to pull it apart. But when you do that, it just creates two new particles of pairs, right? You can never observe a quark by itself. Right? The strong force is truly strong. It's so strong that it will create particles in order to compensate for the fact that you've broken them apart, right? The force is so strong, the energy that you have to put into the system to break them apart is so great that it magically creates new pairs of particles, right? And no matter what you do, you can't get around this, right? No one's ever seen a quark by itself. This is impossible to pull them apart. There's always a new quark that gets formed, and they form pairs. So this is why, what this means is that nuclei are extremely strongly bound. Right? You need a lot of energy to break them apart. Okay. So, not surprisingly, we won't have to worry about that in this class. Right? We're going to assume that nuclei, the amount of energy you have to break a nuclei apart is so significant that basically anything in chemistry is never going to bother. Right? The nuclei, the protons and neutrons in an atom are basically steady state. Right? Basically nothing you can do to them at a chemical scale. Right? You have to blow your molecules apart, remove all the electrons, break all the bonds and stuff before you even get close to the energy you need to manipulate the nuclei. Right? This is why, for instance, fusion, taking two deuterium atoms together to make energy like the sun does, is so damn hard to do, because you got to fight against this to fuse two nuclei, right? You got to take one nuclei and another one and smash them together and get them to stick. That takes a lot of energy. So that kind of chemistry is very rare, and it requires very, very high energies and very high temperatures. Any questions? I have one more force we haven't talked about, the weak force. So the weak force is the reason why, is the force that mediates. Now, as you might know, some nuclei do fall apart, right? There's something called radioactivity, right? Nuclei, big nuclei, like radioactive nuclei, they have unstable nuclei, right? They fall apart. Once a nuclei gets big enough, you have enough neutrons, it becomes unstable. And the weak process is what mediates that. So this mediates nuclear decay. Not surprisingly, because the weak force is so weak, you don't very often see nuclear decay. Right? You only see it in big atoms, really heavy isotopes, things that have way more neutrons than protons. And typically, you want to keep the number of protons and neutrons equal, because a neutron always wants a proton buddy to stabilize it. So when you make atoms of a lot of neutrons, they tend to be very unstable because the neutron's unstable. And the process that mediates that decay of neutrons and nuclei is the weak force. And so a really, really common example of a process that is mediated by the weak force is the decay of carbon-14, right? Radio dating, right? We use this to date fossils and stuff. Right? And this process is mediated by the weak force. And when 14 carbon breaks down, it breaks down into nitrogen-14. It releases an electron and a particle called a neutrino. So this is interesting. So I said this is a weak force, but we've generated a particle that interacts via the electromagnetic force here. Right? So there must be some electromagnetism occurring here, right? Because we're releasing a particle that is mediated through the electromagnetic field, or the electromagnetic force. And then there's this other particle we haven't talked about called a neutrino. And a neutrino, there are three different kinds, and I'll show you that on the page before. Is a very, very small particle, almost massless. It's not exactly massless, but it's tiny. That only interacts via the weak force. All right, so the only way that neutrinos can interact with other things is through the weak force, which I said is a very weak force. So detecting neutrinos can be very, very hard because they don't interact with anything, right? Imagine you want to create a detector that detects electrons. Well, that's really easy. It's called a CCD camera, right? A camera can detect electrons, right? Because light and electrons interact with each other, right? So if you have an electromagnetic detector, it's really easy to find electrons. But what do you do if you, how do you measure something that isn't detected through electrons or through electromagnetic field, right? The neutrino, it's very, very hard to detect, right? And there are a number of what are called neutrino observatories throughout the world. There's a really famous one in Japan. There's one buried underground at the South Pole. There's one in Mississippi, I think. There's a couple of other ones. They're called neutrino observatories. And they're giant water tanks buried deep underground, right? Giant water tanks. I think the one in Japan is like 20 million gallons or something like. It's a huge, huge facility, buried deep underground. And it's filled with as pure of water as you can make. It's actually heavy water, D2O, filled with D2O, and they have along the walls of this giant water tank are detectors that detect radiation, right? There's all these mirrors and absorbing materials all over, all these detectors and stuff like that, 360 degrees around the water. And what happens is that when a neutrino passes into the observatory and it hits, it's moving very, very fast, right? So it's moving around the speed of light, and it's moving very fast. If it hits a deuterium atom in the water at very high speeds, it bounces off the deuterium and it emits a photon, right? The scattering of an electron off of a nucleus of our water molecules emits a photon, and those detectors around there detect those photons. Okay, so we don't detect neutrinos directly. We detect the result of them scattering off of particles, which happens very, very rarely. All right, so the first year that the big neutrino observatory opened in Japan, the estimate was the flux of neutrinos through that, right? How many neutrinos pass through that observatory every second? It's billions. Billions of neutrinos a second, right? So you've got billions of things coming in a second. You should imagine the signals must be booming. The first year, they measured 17 of them, right? So they had trillions and trillions and trillions of particles pass through here, and the probability of a neutrino scattering off of an atom and creating a photon is so rare that they only saw 17 photons. Right? Things have gotten much better. Now they're detecting hundreds a year, thousands a year. Much easier to do that now. But back in the day, it was very, very hard. And the reason why is because the neutrino only interacts through the weak interaction and does so very rarely. So these particles are constantly passing through you. The sun is a neutrino factory. It makes something like 10 to the 30 neutrinos a second. Right? The sun is constantly emitting neutrinos. They're constantly passing through you, but you would never know it because they don't interact with anything in your body. Right? And there's 3 different kinds. I'll show you that on the thing. And what's really cool about them, so there are 3 different kinds. It's called the electron neutrino, the muon neutrino, and the tau neutrino. I don't know why they're called that, but they are. I think they come from different, actually I think they were discovered by, this one is through electrons, this one through muons through taus. They're just generated. They're all charge 0, right? Which means they don't interact through the electromagnetic interaction, right? Because they don't have charge. They're all spin 1/2. And if you look at their masses, right, the electron neutrino is at most 1 electron volt per c squared, right? It's tiny. In fact, we don't actually know the masses of them. We know they have masses, but we can't measure them. They're so small. We know that the tau and the muon are slightly larger by a factor of 1,000 or so, but we can't actually measure them. All right? We just know that they have masses, and the reason why we have masses is very interesting. So very recently, last 10 or 15 years or so, people have discovered they oscillate. They change. An electron neutrino will get created, and it'll oscillate to a muon, it'll oscillate to a tau. They'll interchange with each other. One neutrino will move between the different types. And the only way you can do that is if they have mass, it turns out. So the neutrinos are very interesting. They're unsolved. An unsolved problem. We don't really understand how neutrinos work. We just know that they exist. They probably have a mass. They oscillate between each other. They're very fluxional little particles. So anyway, so those are the particles. Again, we've already talked about the carriers. One thing that's very interesting about the force carriers, you notice the gluon and the photon don't have a mass. They move at the speed of light, right? That's the point. The only things that can move at the speed of light are things that don't have mass. Right? So the photon always travels at the speed of light. It has no mass. It has no charge, thank God. But it has a spin. A photon has a spin. And the spin states, we'll talk about this, about a photon, are actually the polarizations. So -1 and +1 are circularly polarized light. That's where the wave of the particle moves like this in a circle. So if the photon's going in this way, circular polarization means that the wavefront is moving in a circle around its propagation vector, circularly polarized light. And then spin 0, the other state is linearly polarized. So the wave is moving like this. It's not rotating. Okay, so the photon has spin as well. You'll notice, though, that the bosons, the bosons that interact with the weak particles, W and Z, they are huge particles, right? They're about 90 times the size of a hydrogen atom, or 80 times the size of a hydrogen atom. They're very, very high energy, right? And that's why the weak interaction is so weak, is that in order to transfer force of the weak interaction, you have to create a particle that's very, very high energy, and that's very rare. Right? So the larger the particle is, the harder it is to make, and the rarer those interactions happen. Meanwhile, the photon and the gluon, they have no mass, so you can just generate them whenever. Right? They're massless. So that's why with photon, we see so many photons constantly, right? There's trillions of them in this room at this very moment, transferring through, because they're massless. It's not hard to make a photon. You can make a photon of any energy you want. One last particle I haven't talked about. The Higgs boson. This was discovered just 10 years ago. It's been hypothesized for about 40. But as you notice, it's a very, very big particle. It's the biggest one here, 125 gigaelectron volts. Right? It's 125 times the size of the hydrogen, very, very high energy. The Higgs boson, in some ways, is the connective tissue of the Standard Model. It brings everything together in one unified package. And there's something that's really interesting that happens that the Higgs boson mediates. Right? The question is what does it do? If you notice, it's falling under these force carriers. What is the force that the Higgs boson carries? Right? I've explained that these carry the strong force, the electromagnetic force, and the weak force. So what does the Higgs do? Well, there's something that happens that people discovered about 30 years ago, is that if you take two particles together and you put them at an energy, very, very high energy. So if you have an energy scale, so at E scale, so the scale of the energy of your interactions or your collisions is about 250 gigaelectron volts. All right, so you're going to slam these atoms together, these protons or whatever, together really, really fast, really, really high energy. Right, this is what they do at particle accelerators. At this scale, the electromagnetic and the weak forces unify. They become one. So at energies higher than 250 gigaelectron volts, really, really high energies, there's no difference between the electromagnetic force and the weak force. So the same thing. But when you drop below 250 gigaelectron volts, they become two different forces with two different sets of particles, right? The electromagnetic force is a photon-mediated system, and the weak force is the W and Z boson-mediated system. At energies above 250, they all merge together into one. Everything interacts exactly the same. They unify. It's called the electroweak interaction. And when you go below 250 gigaelectron volts, they break apart to two separate forces with two different sets of particles, right? The photon is a massless particle that interacts with the electromagnetic field, and then you have two massive particles, a W and a Z boson, that interact with the weak. So they split apart. You might wonder, okay, well that kind of sounds like a phase transition, right? Right? If you think about, remember when we talked about for the students that were in class last semester, we talked about the critical point in a gas system. Remember, the critical point is where the distinguishing factor between a gas and a liquid disappears. Right? If you're below the critical point, gas and liquids coexist simultaneously, and above the critical point, you only have one fluid. Exactly the same process as this. So at 250 gigaelectron volts, the universe magically has a phase transition that goes from one component, right, the electroweak component, a unified force with a unified set of particles that all interact exactly the same way. And then you drop below 250 gigaelectron volts, and there's a phase transition, and you split into two phases. You split into an electromagnetic phase and a weak phase that have two different types of interactions. They interact completely separately, as if you have two different types of particles, right? Two different states of particles, right? You have two different phases. Right? This is a bona fide phase transition. You can model it as a phase transition. Of course, the question is what is the object? Right? Every event we've talked about so far, there's been a particle that mediates that event. Right? The electromagnetic force is mediated through the photon. The weak force is mediated through the W and the Z bosons. So what mediates this breaking, this phase transition? That's the Higgs boson. The Higgs boson gives W and Z a mass. And it turns out that once you do the math of this, this propagates downwards. That the Higgs boson actually guarantees that all particles of mass have mass. All right, so the Higgs boson, the mechanism that the Higgs boson provides, is that once you drop below the scale, all of the low energy particles that you know and love, ones that are massive, have mass because the Higgs boson gives them mass. All right, so the force, if you will, that the Higgs boson mediates is mass. All right, it's the thing that creates mass. That's a bad way to put at it, but rather it's in some ways it's the representative or the carrier of mass, if you will. Right, so it's really, really important. Right, if you don't have the Higgs boson, nothing has mass. Right, so the Higgs boson is that thing that ties everything together. Right, it brings the electromagnetic and the weak forces together. It gives gives the electron its mass, the bosons their mass. It's what gives the stability to the proton, the neutron, and gives the stability to the electron. Right? That's why the Higgs boson is so important. That's why they called it the God particle. It's because in some ways it's the omniscient particle of the Standard Model. It's what determines everything around it. It's the ultimate particle that determines the entire structure of the system. I don't like that term, the God particle, one, because I'm an atheist, but two, it also implies that the other particles are subservient to the Higgs boson, which I disagree with completely. They're all part of a combined whole. This is a collective system. All of them are equally important. Okay, so that kind of puts us through most of the important particles, right? We've done most of the Standard Model in like one day. What I want to show you here at the end of the class, in just the last 5 minutes, is a picture. What I want to do is I want to take all this information and I want to put our position in this class in context in these many energy scales, right? We've gone from particles that are barely massless particles, low energy particles, all the way up to particles that have massive energies that you can, that are representative temperatures that are, trillions and trillions and quadrillions of Kelvin, right? We've done this huge scale of energy that we've looked at. Where does chemistry fall into place? Well, last year I found this picture on Twitter, and I love it so much that I want to share it with you. So I want to talk just briefly about this picture, and it helps us put us in the context of where chemistry lies in the physical world. So this is a plot. The scales are kind of weird, but let's go through it. So here's a plot of the log of radius of the size of a system in centimeters, right? So this is like this. I think this is log 10. So this is 10 to the 50, 10 to the minus 40 centimeters, right? And here we have masses in terms of giga electron volts, or masses in terms of solar masses. So log of 0. This is the size of the sun. Right? So this is 1 solar mass. This is 10 solar masses. This is 100 solar masses. Right? That's a useful scale for astronomy. So what this is, and then the top scale, let me just look, I forget what it is. It's an energy scale as well. Oh, it's the size of the radius. Okay, so we can look at this. So this is a nice scale. We can compare let's do it in terms of solar masses, right? So this is the size of the sun right here. And this is the physical radius of the object we're studying. And this is a plot of literally everything. This is literally everything, everywhere, all at once. Right, so let's pick in, for instance, here. Let's go along this line right here. This line, so what would that represent? Really, really small objects, right? They have low radius and low mass, right? And there's this line here that's called the quantum limit, the Compton limit. And what we find is that all the subatomic particles that we know lie on this line, right? Here's the photon, here's the electron, here's the proton, here's the neutron. Here's the W boson, here's the tau electron, and here's the Higgs boson. Right, so all of the physics I'm talking about and the grand scale of the universe, which is what this figure represents, is just a really, really small line right here at the bottom. And it turns out that anything below this, like this Compton limit, we can't actually measure those things. Okay, so that's beyond our limit of measurement. Okay, so these things lie on that limit of, basically this is the small limit of the universe. And as you can see, the Higgs boson and all of these things actually contribute a very, very small fraction of the entire energy and size scale of the universe. Right, so let's continue. Right, so let's go up in mass at constant radius. Right, so as we start to go up in mass, we get atoms, we get viruses, bacteria, fleas, humans, whales. Then we get to the moons, the Earth, the sun. Right, and then we get to things that are so large, right? We start to get to the black hole limit. Right, there's a mass. The maximum mass something can have is limited. Right, and once it gets so big, it'll end up collapsing into a black hole, and that's ultimately your limit. Right, so all of our mass is defined by this limit. Right, so the entire observable universe, if you will, exists in this small triangle. Of course, it spans something like, what is that? Like multiple orders of magnitude this way, multiple orders of magnitude this way, right? But it's still a small fraction of the energy scale and the size scale. And so the question, of course, is where is chemistry on this list? Right? Well, this is all gravitational stuff right here. Right? So we don't have to worry about that. Here's biology. Right? Biology is right here effectively. Here's bacteria, COVID, virus. Right? Those are kind of beyond chemistry, if you will. Right? We're starting to get biological systems. Here's atoms, right here. Right? So everything in chemistry that we're going to talk lies in this tiny little sliver right here. Right? Atoms, molecules will be right here, and now here are macroscopic objects like viruses and bacteria, right? Which are conglomerations of molecules. Right? So chemistry lies right here in the middle. Right? And that's the only thing that, right? And what we'll learn is, and so if we look at what's relevant in that limit, right? Well, the only things that are relevant in the quantum scale at that limit are the photon, the electron, and the proton and the neutron. Right? So what does that mean? Well, that means that chemistry is defined only by the electromagnetic interaction. Right? This is the strong force here, for instance, right? We're way past that. We're way weaker energy than that. And obviously gravity, this is where gravity is dominant up here. We're nowhere close to that. We're 40 orders of magnitude away. Right? So chemistry is just this tiny little sliver right here in the universe. And that tiny little sliver right there is just the interactions, due to the interactions of the electromagnetic field. All right, so chemistry is electromagnetic theory. All right, we won't have to worry about the weak. We won't have to worry about the strong. The weak interaction and the strong interaction are here. Right, and we won't have to worry about gravity because that's all up here. Right, but all of these things are interconnected. Right, I can draw this plot and I can put all of them on the same scale. Right, this is why people think that all of these theories have to come together. All these forces have to be unified because everything kind of falls on a continuum together in a really, really smooth way, right? Everything are lines. It's not like there's complicated patterns here. Right? Everything kind of falls into categories and they're all kind of distributed kind of isotropically along these lines. But I just wanted to give you a sense of how small the chemistry world is. Chemistry is right here, right there. And the energy scales we've been talking about, 200 giga electron volts, the Higgs boson's 125, right up here. The chemical energy scale is about electron volt, right? The binding energy of a hydrogen atom, the electron and proton, is 13 eV, right? And the bond strength, typical bond strength between two atoms is about 4 eV. All right, so most of chemistry is on that energy scale of about 1 to 20 eV. Right? And that's just this tiny little region right here. Right? And that's all electromagnetism. All right? So I've spent this entire week, this entire lecture talking to you about all these odds and ends, but really we only care about electromagnetism. All right? So we're going to really focus in on protons and electrons and neutrons. And then next class we'll come back to this idea. Okay? All right, have a lovely day, guys. Sorry I ran late.